Thank you, and it's really great to be here among my peers. It's so nice to get a chance to talk to you all. The project that I'm talking about was started just last summer, and it's only partially complete, so the results are not as complete as I would like, but I wanted to make everybody aware of the project that I was working on. The motivation for this is quite obvious. The lake in 1984 was at near capacity, and you fast forward to 2016, and you can see the dramatic change in the lake surface area. And that has exposed more than 550 square miles of lake sediment that has started to blow as a dust source for the surrounding communities. The dust storms, there was a really particularly large one that happened just last November 26th that actually reduced the visibility at the airport to less than 4 miles, ended up impacting the entire Salt Lake Valley. And the dust season itself, from dust coming from off the lake, observed just last year, the first dust episode that I observed coming off the lake itself was April 22nd, and this November 26th was the last episode. So the dust episode window is actually much larger than I originally thought it was. And it's not just associated with cold fronts and wind changes, but you also have convective activity, downdrafts, downbursts that can actually generate dust off the lake. And surprisingly, I also noticed that dust devils out on the lake itself are a source of dust to the atmosphere as well. The goals of this project are to basically document the soil surface crust characteristics over the entire lakebed surface and to identify hotspots of where on the Great Salt Lake those dusts are most likely to be originating from, and then to follow that up with determining if there are any heavy metals in that dust that are above what we would see in naturally occurring soils. And eventually, we want to create a data set that can inform emission models, and in particular, looking at the PM2.5 to PM10 ratio, of course, the elemental composition, threshold wind velocities, and ultimately the index of refraction, because once this dust is deposited in the snowpack, it has major implications on the radiative balance in the snow itself. So the methodology that I used to collect these soil samples was the incremental sampling methodology, and the basic idea is to carefully plan your collection and analysis in such a way that you get reproducible and representative samples. I obviously can't sample over the entire lake bed, so you take a representative sampling. And what we did is we set up with GPS coordinates for sampling locations, and then we go out and visit those sites using the GPS. And we collect between 40 and 60 discrete soil samples from a decision unit or a subunit, and we composite those into a single sample. And we obviously take sufficient blanks and replicants and co-located samples to be able to characterize the uncertainty of the measurements themselves. And to put that into perspective, we have the Great Salt Lake, and for this project, we've divided this up into 10 different decision units. These are contiguous areas that are likely to be impacted by the same type of sources. The study so far has focused on Decision Unit 1, Decision Unit 2, and Decision Unit 3, the ones that are closest to the Salt Lake Valley. But as soon as the weather allows, we'll be going back out to collect more samples across the other decision units as well. We're focusing in on the southern half of the lake first, and then moving toward the northern half of the lake after that. So this is an example of the sampling locations from some of the subunits in Decision Unit 2. These gridded cells in this case are about half a kilometer apart. So in each one of these cells, which are predominantly about 4 kilometers by 4 kilometers, which is about the resolution that we often use on the WRF model. The spatial resolution in some places on the lake is down to 250 meters, but for most of it, it's about 500 meters between sampling locations. So here's my mode of transportation. It's the University of Utah Dust Devil. The reason I've chosen to use this mode of transportation is shown on the right, where you have actually two sets of tracks. You have an ATV track, and then right in the middle of that you have the footprint from the bicycle itself. In good conscience, I couldn't actually go over the entire lakebed with an ATV and disturb the surface, because it's just, that's hard to swallow considering what I'm trying to study in the first place. It's a lot of work, but you see a lot of things, and you learn intimately the different characteristics of the surface that are out on the lake. Statistics so far, we've completed sampling on 23 subunits, completed Decision Unit 1 and Decision Unit 2, and have started on Decision Unit 3, and that represents about 26% of the entire 550 square miles of the lakebed. We have a total of more than 1,000 soil samples have been collected. More than 650 kilograms of soil has been processed, 405 miles, and only one flat tire. That was a good thing. That was a bad day. At each of those locations in those subunits, those 40 to 50 spots, we characterize the soil surface observations in terms of vegetation, surface crust, cobbles, whether or not the surface is erodible, there's sand, are there visible fines that are can be blown. There are biomats and there are bioherms. There's lots of black organic soil, and you can see. And just to give you some examples, thick crust. So here we have an example of thick crust. This is very rare on the Great Salt Lake. This actually represents less than 1% of the surface area that I have encountered out there. It has a very thick crust, and it's basically impervious to wind-blown emissions. Looking back, we also have this erodible surface crust. Here's an example, essentially, of a thin layer of surface crust that is curling up at the edges. It's easily disturbed and often generates fine dust associated with it. And the other thing that I want to focus in on are the visible fine particulates, which are basically, you do the boot test. You kick the dirt, and does a dust plume come up? And it's a very nice little test. I have a little video of it, but the video's not working, so I'll skip that. But you get the idea of the boot test. So these soil samples, at each of those locations, we collect 3 samples. We collect 2 samples of the surface crust, 1 primary sample and 1 within 2 meters, kind of randomly, to kind of look at the representation of the horizontal homogeneity of that. We also collect a subsurface sample. So in case the top layer completely deflates, then we have an idea of what would be the next source of material to the atmosphere. These samples are taken to the lab. They're dried for 24 hours at 105 degrees C. They're sieved in small mass increments. And then ultimately, I resuspend the smallest fraction from the sieve and sample with a PM10 sampler in order to collect the material for analysis. So here's one of the first results, which you're looking at the map of the silt and clay fractions. So this would be the particles that are less than 75 micrometers. Eventually, I'll be able to get this right down to a fraction of the soil, which is PM2.5 or PM10. Not quite there yet. But you'll see that there's actually quite a bit of variability. So down in the southern part of the lake, less than 2% of the total soil is contained in the silt and clay fractions, and that increases as you move up towards Goggins Drain, which is an inflow area, and also up here near the inflow for the Jordan River are the places where we have the highest percent of silt and clay. And as you go around the backside of Antelope Island, it reduces back down to very little silt and clay material along the way. If you look at a standard soil texture analysis, all of the samples that I have collected so far fall in this extreme corner. It's basically sand, with a very small amount of silt and clay associated with it. And from all of our perspectives, that's a really good thing, because if we had significant amounts of silt and clay out there, the potential ramifications on our local air quality would be much more severe. So one of the questions that everybody wants to know is, where is the soil actually blowing from? And these are the locations where boots on the ground have basically identified as potential dust source regions. The southern shore doesn't have very many sources. As you move up into what used to be Farmington Bay, that's where a congregation of these hotspots actually are located. And because we're mapping these out with GPS, I'm actually going to be working with Dr. Phil Dennison and a graduate student, Adam Clark, to combine this with a digital elevation model. So we'll actually know what essentially a lake level would be required to cover up these potential hotspots, or to do a PDF of that sort of thing. And that would be very useful moving forward, as well as we do this for the entire lake. The things to note about those hotspots: they're preferentially located close to stream entrances in areas of sparse vegetation. There's actually a fair amount of vegetation on the lakebed surface, and the places where there is vegetation tend to accumulate some of those fine materials. And they also occur in heavily disturbed areas. And I'll give an example of that. The northern part of Antelope Island is probably one of the most heavily disturbed beaches on the entire thing, and it's almost all essentially deflatable material up there from the disturbance. And that has implications on ATV use and other things that people would do out on the lake surface itself. The other thing that we've noticed about this is that you can actually use these aerial images to kind of predict where the soil is actually going to be deflating from. It's hard to see on this, but these areas where you actually have deflation from these hotspots are actually bright on the aerial image, related to the higher fraction in some cases of the silt and the clay, and also associated with areas right near vegetation along the way. And if you just want to look at the other side of that, is where are thick and moderate crusts located? So these are the places where we have that. It's about 4.2% of all of the samples I've collected have a moderately thick crust, and only 1.1% have a thick crust. I had expected a lot more of thick and moderate crust when I went out there, and it's actually pretty rare along the way. Analytical techniques so far, we're basically using ICP-MS and synchrotron X-ray fluorescence of the resuspended PM10. It gets a total of about 51 elements above the minimum quantifiable limit. We'll eventually be doing particle size distributions, index of refraction, and mineralogy. And just to give you a little quick teaser, if we look at the spatial gradient of PM10 copper, we have decision unit 1, which is basically down near Grantsville and Tooele, moving up towards past the Kennecott tailings pile and up into Farmington Bay. And you'll see that there's a pretty big difference in copper as you move through there, which would be influence of the Kennecott tailings pile. So that's one essentially thing that we noticed. It's actually only about a factor of 9 difference between the background and the area adjacent to the tailings pile. I actually had expected it to be a lot more than that. Another example is zinc. Zinc actually has 2 hotspots, and they're both associated with stream inflow areas to the Great Salt Lake. And there's a lot of other elements here that I could go through, but given the time, basically just want to give a teaser on that. The other thing that we're doing is we're looking at the chemical composition of the mineral dust and comparing it to what has been observed at Hawthorne and Layton to kind of see, is the mineral dust that we see from the Great Salt Lake significantly different from that we're observing in the speciation network? And I just will say that the 2 elements that have kind of gotten my attention as being elevated from the lake soil are actually arsenic and chromium. Chromium, the speciation of the chromium is obviously crucial to determining whether or not that poses a significant health risk. But moving on to the next steps for future work, obviously, I want to complete the sample collection of the other 75% of the lake bed, so everything I do here is basically kind of preliminary. But where we're really going with this is we want to do a health risk assessment for carcinogenic and non-carcinogenic species that we're seeing out there, and to use the meteorology to get realistic exposure frequencies along with the measured elemental composition, so we can answer the question that everybody wants to know. Is there something out there that we need to be worried about from a health perspective? And then, of course, from a basically trying to combine the data with the digital elevation model to kind of see potential remediation efforts in terms of lake levels is one of the things that we could do. I'd like to acknowledge funding sources for this. It's jointly funded by the Utah Division of Natural Resources and the Division of Facilities and Construction Management, which is primarily responsible for construction of the prison, which is out on a perfect site for dust, right between the Kennecott's tailings pile and the lake. So thank you very much.